Hello students. In this lecture we're going to learn about mechanical work and what it can do to objects with mechanical energy. We're going to analyze the situation and determine if mechanical work will change the total mechanical energy of an object. And you should also be able to solve problems using the relationship between work, force, and distance. And there's a second relationship that we're going to learn about, and that's the relationship between work and total mechanical energy. So let's take some notes on mechanical work. Mechanical work is what we call the transfer of mechanical energy from one object to another. So energy can be transferred, any kind of energy can be transferred from one object to another. But when we're specifically talking about mechanical energy, GPE, KE, or EPE, then we call it mechanical work. So work results from a force. And we're going to learn a lot more about forces later on in the year, but for now, let's just call a force any push or pull. If I'm pushing on an object with my own hands or through a rope, or maybe gravity pulling an object down, or anything like that, any push or pull on an object, we're going to call a force. And if I apply that force over a distance, so let's say I push a chair across a distance of a meter or something like that. Or maybe the engine in my car acts on my car to push it over 10 meters, 15 meters. I need a force and a distance, and if I do have both of those things at the same time, then I'm going to be able to change the total mechanical energy of an object. Now this is a change from what we talked about before. Up until now, we've been analyzing situations mainly where the total mechanical energy doesn't change. We've been talking about pendulums and roller coasters and other physical devices where there is no friction, no air resistance, nobody pushes anything, and the statement that we're making is that no mechanical energy was entering or leaving the object, and therefore the total mechanical energy would stay constant. Now that's going to change. Now we realize that the total mechanical energy is only constant if there's no work. We can put this into an equation. Work equals force times distance. W is for work. And force is in a unit called newtons. We don't really need to know right now how much a newton is. We'll see some examples in class, but this is just the units of newtons. How much force, how hard am I pulling on something? Oh, 500 newtons. Could be a push or a pull. The strength of a push or pull we measure in newtons. Distance we already know that we measure in meters. And this symbol right here, this triangle, is the Greek letter delta, and it stands for change. So we've already seen ME to stand for mechanical energy. When I put a delta in front of it, delta ME means change in mechanical energy. So we can see that the units of work are also joules, because work is just mechanical energy moving from one object to another. How much energy are we moving? We can move 100 joules, 200 joules, any number of joules. So the unit of work is the same as the unit of energy, and that is joules. Because work is the change in mechanical energy, I can restate that as something called the work-energy theorem. And that's actually just a little bit of logic. If I have some sort of final mechanical energy, MEF, that means the mechanical energy at the end of some process, that's going to be equal to the initial mechanical energy, whatever mechanical energy I had at the very beginning. Initial just means beginning, plus the work done on the object. So MEI, mechanical energy initial, the initial mechanical energy is whatever total mechanical energy I have at the beginning. If I do some work on that object, I might be giving it more energy, and whatever energy I give to it, it has that as its final mechanical energy. So we can see that work, or mechanical work, is what can change the total mechanical energy of an object. There's a couple different ways that it could go. We could have positive work, And this means mechanical work that is transferring energy into an object. And we can tell because the object is gaining total mechanical energy. If I take a box and I lift it up to a height and place it on a shelf, I have done positive work on that box because I have given it mechanical energy that it didn't have before. I did positive work on the box, gave it energy. The opposite is also true. Negative work is when we take mechanical energy out of an object. So the object is going to lose total mechanical energy. Typical sources of negative work include air resistance and friction, because what they do is actually take some of your mechanical energy and out of the object and turn it into thermal energy. So let's say brakes, for example, would be another instance of negative work. An example of negative work that we have seen in class and in our other activities would be a pendulum in real life. We've seen that if I release a pendulum from some height above the ground, let's say the ground is right here, and when it swings back around the other side, it may end up lower than where it initially started. With this, the pendulum is going to swing back out, and when it gets to the other side, it might actually be lower. That second height is, in real life, less than the height that it started off at. And when we talked about that in class, we said that the pendulum bob is having to push its way through the air. It's rubbing up against the air, and there's a little bit of friction and air resistance. And now we can see that friction and air resistance are actually doing negative work on the pendulum because it's removing total energy from the pendulum bob. And that's why we end up at a lower height, because the pendulum has less energy. Okay, now I'm going to give you some steps to solve mechanical energy problems. So step one, of course, every time, is you want to write your knowns and label your diagrams, as we've done in previous problem solving. That is always got to be step one. Step two, find the total energy state. That means find all the energies, GP, KE, and total ME, at a point where you have enough information. There's usually at least one point where you can find all of the energies of whatever object is in question. So 3A, step 3A, if no energy is transferred into or out of the object, that means we aren't putting energy in, we aren't taking any energy out, then you know that the total mechanical energy is going to stay constant at all times and at all points. However, if energy is transferred, if you know that energy is entering the object or leaving the object, now we have to consider the change in total mechanical energy. Now we have to consider mechanical work. So we're going to have to use our two relationships, work equals force times distance, or work equals the change in mechanical energy, in order to figure out how much energy was transferred. Your next step, step number 4, is to find either GP or KE at another point based on the knowns. And usually you can use the total energy equation, ME equals GP E plus KE, to find all other unknowns. Let's see this step by step in action. So example 1 here is fairly straightforward. I have a student applying a force of 100 newtons to a rock, which moves a distance of 2.5 meters. What is the amount of work done by the student on the rock, and where did this energy go? Okay, step number 1, as usual, I have to write my knowns, and it always helps if I can draw a diagram. So this one's really simple. I have a rock, and there's a force applied to that rock of 100 newtons. I'm going to say F equals 100 N. N is the units that we're going to use for force. And this distance that the rock moves is going to be 2.5 meters. And the question is, what is the amount of work done by the student on the rock? Where did this energy go? In order to find the amount of work done, we can use our relationship W equals FD. Work is equal to the force times the distance that the force is applied through. And we just plug in what we know. We know that there's a force of 100 newtons applied through a distance of 2.5 meters. And if I multiply that out, I get 250 joules. So that is the amount of work done by the student on the rock. A very simple, straightforward example. We didn't even have to use our total energy relation. But we are also asked, where did this energy go? So we can say mechanical energy was transferred from the student into kinetic energy of the rock. Because we moved the rock, we moved it through a distance. And now the rock has that energy. We transferred it from one object to another. Let's try another example that is going to be a little bit more complicated. So example number 2, a 7-kilogram box is pushed across a level floor with a force of 50 newtons for a distance of 10 meters. It is then lifted to a height of 2 meters. What is the total work done on the box? What I'd like you to do is pause the video, try this example, and then wait for the solution. Okay, in this case, it's really going to help us if we draw the problem properly. So I'm going to make a little shelf because I know this object is going to be lifted to a height. I have a box down here on the ground. It is pushed across this floor with a force of 50 newtons. And this distance right here is 10 meters, so I'm going to put a D equals 10 meters. And then it's lifted to a height of 2 meters. Clearly I haven't drawn that to scale, but at least it shows me where my different variables are. Now, two things are happening here. The first thing that's happening is that we have a force acting through a distance. That's one thing that's happening right over there. The next thing that's happening is that I'm adding mechanical energy to the object by giving it height. I'm giving it gravitational potential energy. So I know that I'm going to want to write down those two relations because they're probably going to come in handy. Let's write them both down. Work is force times distance. And I know that the gravitational potential energy equation is going to come in handy because that is the kind of energy that I'm giving to this box in that second part right over here. And I'm probably also going to need the fact that work is the change in mechanical energy. So let's solve through what happens. So I'm gonna label this as step 1 and this is step 2. Step 1 is where the box is moving across the floor, and step 2 is where the box is raised to a height of 2 meters. In step 1, we know that the work done in step 1 is a force times the distance. So I'm just going to plug in what I know. 50 newtons times 10 meters is 500 joules of work done on that box. So that's fairly straightforward. That's just multiplying two numbers together. The second part is realizing that when I'm lifting the object onto the shelf, I'm giving it mechanical energy. And any change in mechanical energy that the box didn't have before, that has to be due to mechanical work. So there's a second bit of work that happens here, and it's equal to the change in mechanical energy of the box. What kind of mechanical energy did I give the box? I gave it GPE. So let's use our GP equals mgh. the mass of this box is 7 kilograms, and oops, I never wrote that on my notes. Always write that on your notes. My mistake. So let's put in 7 kilograms times 10 meters per second squared, which is the acceleration due to gravity, times a height of 2 meters. So 10 times 2 is 20, and 70 times 20 is 140. So this equals 140 joules. And if I want to get the total amount of work done, I'm just going to add up the two segments of work done. The first segment from pushing the box across the floor with a force of 50 newtons across 10 meters. And the second bit of work that I did was to lift it up to a height and change its total mechanical energy. So let's just add those two together. I'll get 500 plus 140. Well, that's some easy math. 640 joules of work. That is the total amount of energy that was transferred to the box. Okay, let's see an even more complicated example. This time we're going to see what work can do to the total mechanical energy of an object and how it can affect an object's motion. So here's example 3. A roller coaster with a mass of 550 kilograms is traveling at 14 meters per second as it approaches a hill. Friction will do negative 10,000 joules of work on the roller coaster as it climbs. What is the maximum height that the roller coaster can reach? I'd like you to pause the video and set up this problem, draw a diagram, write your notes, write down any relationships that might be important, and try and find the solution. I'll do out the solution in just a moment, so pause the video. Okay, let's see how you did. Step 1, always, write your notes. In this case, I'm going to want to draw a diagram of my roller coaster. I have a roller coaster approaching some hill. That roller coaster I know is moving, and it has a velocity of 14 meters per second. It has a mass of 550 kilograms. Other things I know that the work done by friction is going to be 10,000 joules, and I'm looking for a height. How high can it reach on that hill? Things I know are going to be important. Well, the roller coaster clearly has motion at the bottom of the hill, so I know I'm going to have to use my kinetic energy relation, or at least it's a pretty good bet, so I'm going to write it down. My roller coaster is going to gain height, so I want to write down my GPE equation, because gravitational potential energy is the energy associated with height. I have work happening. Friction is doing some negative work, and so I'm going to write down the fact that the amount of work done is the same as the change in total mechanical energy. So once I've written those down, I can proceed to my solution. Okay, let's see what this roller coaster has. So at the very beginning of the situation, the roller coaster is at the bottom of the hill. So bottom of hill. If it's at the bottom of the hill, I can assume its height is 0. So GPE equals MGH equals 0 joules. The roller coaster is moving 1/2 mv squared. So 1/2 550 times 14 squared. So if I multiply that together, that's 53,900 joules. So my total mechanical energy at the bottom of the hill, GPE plus KE, is 53,900 joules. That's the total amount of energy that this roller coaster starts with. Now it doesn't get to keep all of that energy because friction is going to do work on this roller coaster. And remember, work being done is energy transfer into or out of an object. In this case, the work done is negative, so friction is going to remove 10,000 joules of energy from the roller coaster. I know that my new mechanical energy is going to be the mechanical energy that I had initially, my initial mechanical energy, plus the work that I do. And in this case, the work is negative, so I want to subtract 10,000 joules of energy. So my new mechanical energy is just 53,900 minus 10,000, which is 43,900 joules. This is my new mechanical energy after friction took away 10,000 joules. That's what work is. Either we're adding energy or we're taking it away. So now, if I want to get as high up as I can on this hill, how high can I reach? What is the maximum height that I can reach? Well, I would reach the maximum height if I'm spending all of my available energy on GPE. So I'm going to make that note to myself: max height if all ME is in GPE, the energy associated with height, gravitational potential energy. So I'm going to set my GPE equal to 43,900 joules. I'm going to spend all my energy available on height. And we know that GP equals mgh, so 550, 10, and height is unknown. So let's see. Now it's just algebra. 550 times 10 is 5,500, so I want to divide through on both sides by 5,500. And if I calculate that out, I get a height of just under 8 meters. This represents how high of a hill this roller coaster can climb, given the fact that friction took away 10,000 joules of its energy. So let me recap, because this was a complicated problem. Step 1, I read the problem to figure out what I knew. I wrote down my knowns, including my velocity, mass, the amount of work done by friction, and what I was looking for, the height. I wrote down the relationships that I would be using. Then, after I had those in equation form, I started with how much mechanical energy I had at the bottom of the hill. I knew that I had no GPE because my height was 0. My kinetic energy due to my 14 meters per second of velocity. And I added that up to get a total mechanical energy of 53,900, which was just equal to the KE. Next step, I looked at how did work affect my total mechanical energy. And in this case, it removed 10,000 joules of energy from my total available, which left me with 43,900 joules. The last step, I use logic to think about the fact that if I want to get to my maximum height, I can only do that if all of my mechanical energy is in gravitational potential energy. So I'm going to set my GPE equal to all of the energy I have available, 43,900. I put that into the GPE relation, GP equals mgh, and then solved for h to get a height of 7.98 meters. Okay, so let's take a look back at our objectives for this lesson. The objectives were to analyze the situation and determine if mechanical work will change the total mechanical energy of an object. So if you see energy transferring into or out of the object, you know that mechanical work is being done if the total mechanical energy is changing. You should be able to solve problems using the relationship between work, force, and distance. That's just our equation work equals force times distance. And you should also be able to solve problems based on the relationship between work and total mechanical energy. That means knowing that the amount of work done is the amount that the total mechanical energy will change.